there are two types of reactions that I always teach together because they are opposites of one another. So we've moved on from balancing. Balancing is still going to be a part of this, but now we're learning types of chemical reactions. So there are three specific special cases that we'll kind of talk about through this. That's what your sticky note is for. Um, Remember when we talked about bad questions? The last sentence out of my mouth was your sticky note is to write your three special case scenarios. Okay. So if you don't know what to do to sticky note, just chill. Just sit there, put your hand down. You don't have a question yet. Whatever question you're about to ask is not a good one. This is all recording. Excellent. A synthesis reaction. Do you know what the word synthesis means? To synthesize, which means to create, okay, or to make. So to synthesize something is to create it. A synthesis reaction is creating a new substance. So in a synthesis reaction, you will recognize these because you will have one product. So synthesis means to make, and it's going to be one product. So don't put this on your sticky note. I will tell you when the sticky note is relevant. So to make one product. So for example, if I have substance A, and then I have another substance, we'll call it substance B. And if we want to be super specific, we could call this substance B2. It's going to be diatomic, and I can tell because it's just two little particles stuck together like that. It's going to come together to form product AB. So a synthesis reaction forms a single product from two or more reactants. The opposite of a synthesis reaction is what we call a decomposition reaction. So it's opposite of synthesis. We used decomposes up here. So when something decomposes, instead of having a single product, you have a single reactant. And then your reactant breaks down into multiple products. So a single reactant breaks into multiple elements or compounds. So decomposition means to break down. And so the example that I have here is if I have compound AB, it would break down into compounds A and B. Or I can switch them and call it A2 plus B. Or if that freaks you out, you can do A and B2. The only reason you know that it has 2 is because the picture is showing you that. This isn't balanced. It doesn't have to be balanced. That doesn't mean that this would be compound AB2. It's okay. I'm just showing you how to read a particle diagram. If there are 2 of them together, it would have a subscript of 2. That's all. And then in these boxes, that's what we're going to write as well. I forgot that part. So A plus B2 yields AB. It's not always going to be diatomic. You could have A plus B yields AB. And then AB breaks down into A plus B. So they are opposites of one another. So when I am looking at something, in my first example, I have calcium oxide and water reacts together to form calcium hydroxide. This one product, I'm using the wrong color, but whatever. One product tells me that it is a synthesis reaction. This is one of our special case scenarios, so this is why I gave you your sticky note. If you don't have a sticky note, you can fit this onto your page somewhere that you have space, but there are 3 special cases that I want you to memorize. So write this, memorize these. Memorize for synthesis / decomposition. first case is if you have a metal oxide. So, for example, what we have here, calcium oxide. So this is special case 1 if you want to note that. So a metal oxide, any metal, plus, what's it being added to? Water. So plus H2O or plus water will yield a metal hydroxide. So metal oxide plus water will yield a metal hydroxide. You need to be able to apply that basic format to any metal oxide plus water that I give you. This also works in the opposite direction, where if I gave you a metal hydroxide, it would decompose into the metal oxide and water. So it's kind of a reversible thing. So you can put the arrow going both ways, which is also why I taught that the arrow isn't not just left and right talking about products versus reactants. It's which way is the arrow pointing. So whatever's to the point of the arrow, that's going to be your products, and the base of the arrow is going to be your reactants. So in this case, you can go both ways. If you're going from right to left, that would be your decomposition reaction, but from left to right is your synthesis reaction. But you need to memorize that general thing. The second special case is when you have a metal oxide plus carbon dioxide, so CO2. And again, this one will go both ways, so double-sided arrow. We'll make a metal carbonate or metallic carbonate. Do you remember what carbonate is? Good. CO3 with what charge? -2. Okay, so metal oxide and carbon dioxide will yield a metal carbonate. I don't have an example of that in your notes right now, but there are examples in your homework. And then the third example, or the third special case, is a metal chloride plus oxygen will make metal chlorate, CHLORATE. So it does not matter if you write this on the sticky note or on your actual notes. I just had the sticky note because I realized I didn't give you very much space to write these cases, and they apply for both synthesis and decomposition. So the way that I wrote them, like if you're reading it left to right, like we're typically reading our reactions, this would be a synthesis reaction, this would be a synthesis reaction, this would be a synthesis reaction. All you have to do to make it decomposition is take it backwards. Your single reactant making these two products, single reactant making these two products, and then single reactant making these two products. So you need to memorize all three of these cases and be able to apply it to any metal following that format. So metal oxides and metal chlorides. Good? Okay. And then down here I have another example where we have magnesium strip reacting with oxygen to form. I'm going to fold that up just so that it's out of the way. Magnesium strip reacts with oxygen to form what? So magnesium, how would I write the formula for that? Mg, okay, good. Do I put a subscript on there? Question, Ronnie? Okay. Say that one more time. I'm not understanding your question. Ask it again. So, how does chlorate? That's where balancing the equation comes into play. If I'm understanding what you're asking, I'm not positive that I fully understand your question, but if it is what I think you're asking, it's because we have to balance the equation. Does that answer it or no? does that make sense? I still don't fully understand what he was asking. Okay, what is it, a balancing thing? Okay. A magnesium strip, so, thank you for asking that. Sorry I couldn't follow it. I'm going to watch the recording back and try to figure out what you were asking me. I'll have a better answer next time. Magnesium strip reacts with oxygen, so magnesium does not need a subscript. Why not? Because it's not diatomic. Good. It reacts with oxygen. Does oxygen need a subscript? Yes, because it is diatomic. Reacts together to form the combination of magnesium and oxygen. So what would that be? MgO, so magnesium oxide. So I'll write the name here, magnesium. Do I need a Roman numeral? No, because magnesium has a predictable charge. It has a +2 charge according to my periodic table. Oxygen has a -2 charge according to my periodic table. So when I crisscross those, I get Mg2O2, but then that would reduce to just MgO. Even though oxygen is diatomic, I don't put the O here because it's only diatomic when it's by itself. It's not diatomic when it's part of a compound. Or it doesn't matter that it's diatomic when it's part of a compound. So then I would balance this one. I have 2 oxygens on this side. I need how many oxygens on this side? 2, so I can kind of cheat it without my RMP chart here. 2 times 1 magnesium, 2 magnesiums. I have 2 of these, 2 of these, 2 of those, 2 of those. We're good. Easy balancing. When it's something that simple, you don't have to show me your work. You're fine. But for the most part, I want you to show me your RMP charts. That way I know you're actually doing your homework. Practice, practice, practice. We'll pick up on decomposition next time.